So with this and all in mind, let's talk about design for injection molding. Now, we're probably more familiar with design for injection molding with, CNC machining or subtractive manufacturing in mind. But with additive manufacturing in mind to produce the mold, there's a lot of like carryover. There's a lot of similar design principles there. So let's start out with a few of these. So for instance, like unsupported walls, ribs, these are the kind of things you need to consider in terms of filleting, in terms of distance between ribs, thicknesses and heights. Also, when it comes to injection molding, it's always recommended to have your wall thicknesses be as close to similar as possible all throughout. But that's not always possible. So if you need to adjust between one thickness down to another, you want to do it very gradually. And so that's kind of what you want to look at. You want to have that length there of that gradual slope just be at least 3 times the change in height between those two thicknesses there. Probably the most classic and well-known principle for injection mold design is draft angle. So you want to have a draft angle of at least 2 degrees. The higher you can go, so if you can go up to 3 or 5 degrees, the better, the easier it'll be to remove that part from the mold. The other thing is filleting your corners. So corners can be an area where you can retain a lot of heat stresses and you can have some quality issues result. So you want to fillet those corners as much as possible. This kind of goes back to what I mentioned earlier about consistent wall thicknesses. So kind of in that upper right, you can see you want to avoid having just like a solid block of material. It's more advisable to have that block shelled out, and aim for wall thicknesses of like 1 to 3 millimeters. And lastly, just 2 things to consider there with engraves and with emboss features. Now, this this slide here is going to cover some design principles that are more in line with using additive manufacturing to produce the mold. So for Brascom's case, going back to that one again with the mass straps. So here we're looking at the front and back of the mold, and what you'll notice is the back of the mold kind of replicates the design of the actual mass straps themselves. And the reason that it's kind of been shelled and cored out like that is, for one, it's not using as much material, and for another, it's going to help conduct heat away better than if it was just like a solid block on the back end. Another thing to consider is scaling the physical part itself. So in CAD, what you want to do is you want to, and obviously it heavily depends on the shop material, but say for that high flow or high temp flow, low viscosity polypropylene, you'd want to scale that by like 2%. So you have your mass strap in CAD, scale it up by 2%, and then do like kind of your Boolean cut operation to perform or actually build the mold itself. And that's just to counteract any shrinkage of the material post mold. Another thing to consider is if you have ejector pins modeled into your mold, what you want to do is you want to model the hole diameter for those pins to be size on size with the ejector pins themselves. That way, after you finish printing, you can just ream out those holes, really control how much material you're removing. And so you're still able to move those pins in and out, but still able to maintain the seal when you actually go to mold that part. If you're using a unit die master for your mold, you want the mold surface to be flush with that die master. And on the topic of the die master, what you want to design into the mold is for the head of the bolt to be flush with the surface of the mold and be directed inward towards the die master, so that the head is on the mold side and the threads are directed back into the die master, just like that. So it's a little bit reverse from maybe what you're used to if you're using other materials.